All right, so this question is question which is 2015 question, a very interesting question on power delivered by the engine. Read it carefully, and then I will discuss this topic also a bit so that you have a clearer theory on how to approach the questions pertaining to variable force. Okay. Now, I hope you've read the question. There is a engine which is moving, and there is a resistive force in picture opposing the direction of the engine. You have to calculate the expression of power and time, and then convert it into a graph. Now, although it looks very simple question, but let's discuss how to solve it. Okay, I'll reduce the size of the image and then write it. Okay, let's talk about this question. So you have a situation. So let me just give you a theoretical perspective. So first you have something like a constant, okay, power scenarios. Okay, constant power. The engine is capable of giving a constant power, and then we write that the power is given by F dot V, and you can see the power, if they're in the same direction, the velocity and the force are in same direction, then it is F V cos of 0 is equal to F multiplied by V. Okay, this is not a vector algebra question. I mean, this is not a vector product. This is just a, okay. Now, if the power is constant, then if the initially when the body starts, right, when you drive the car or an engine, what you do is you have a lot of engine force available because you have to overcome the inertia, but the velocity is small. So therefore initially the force of the engine is very, very high, and the velocity of the engine is small. Okay, now so the force, and later in the game, when the engine is very fast, the driving force goes down. Okay, so you can see there is an inverse relationship of force and velocity when the power is constant. Okay, and this is very counterintuitive because you would imagine that if the force is very high, right, then the acceleration is very high, right, and therefore the velocity is very high. I mean, this is not straightforward, right? So initially the force is very high, the velocity is low, and later on in the motion the force goes down, the velocity increases, because you have to keep the power being delivered by the engine to be constant. So such scenarios where force and velocity are inversely proportional to each other are called as constant power scenarios. Now let's talk about our question. Is it a constant power scenario or not? If I look into the graph number A looks like this. Okay, it pretty much appears like this. Okay, and this is power versus time, and there is no variation of power with time. So it looks like a constant power graph, right? It does actually. But let's see whether this actually is a situation of constant power delivery or not. Or is it a situation of variable power, which means the power keeps on adjusting itself. Okay. Now, the second, okay, so we will talk about it. Now let's talk about the second thing. How do you solve such a question? So these questions are not just to be solved using an equation and that's about it. The first step is always to draw a free body diagram. Okay, so this is your free body diagram. This is your engine force. This is your resistance. Okay, this is your resistance. Okay, and it is proportional to velocity. Okay, now if you notice the first line of the question, it is cryptic, it is not straightforward. It says that the body moves with a constant acceleration. In the case of constant power, the body doesn't move with constant acceleration. In the case of constant power, the body does not move with constant force. The force is high, the velocity is low, the velocity high, the force is low. In our question, force is constant, but there is a concept of resistance also. So therefore, the engine force minus the resistance, let's say it's proportional to V, so I introduce equal to, so this becomes equal to kV. Okay, so for resistive force is kV. I'm putting a negative side because it is in the opposite direction. Right now I'm applying mechanics, is equal to ma. This is uniform acceleration where v is equal to u plus at. Okay, the engine starts from rest and therefore u is 0, therefore v is equal to a into t. So engine force, the engine force is equal to ma plus kv is equal to m into v. A is given by a by t, so, right? So a is equal to v by t. So I'm writing v by t plus kv. So this is your engine force. Now we know the power formula. So power is equal to mass into velocity by time plus kv multiply by the velocity. Okay, so I multiply this with velocity and I get m v square by t plus kv square, and I can convert v is equal to at, so I will get m a square t square by t plus k a square t square. Okay, and this gets cancelled, so I get my total power as ma square t, a is a constant, plus k a square t square. Okay, so this is a parabola. Okay, this is a parabola. This is a parabola we are referring to. Okay, now let's look into the two. So you can see one of the option which is that the power is increasing continuously. This option anyway is a wrong option. It is not possible. Okay, and we have also seen that in this particular case, this particular constant power scenario is not applicable because the expression of engine force will give you a velocity which is this v velocity, right? So you can see the force and the velocity are not linked to each other in an inverse manner, right? So force is equal to p upon v, right? Inversely proportional. Here the relationship between the force or the power and the velocity is very different. You can see one of the expressions I calculated. So p is equal to this, right? So it's v square, not inversely proportional to v, right? The force. So it's a different scenario. So we can ignore this one, which is a constant power scenario. So the point I'm trying to make is, it is not just that you solve a question. You should understand what is the essence of the question, right? The essence of the question is it's not a constant power scenario, which is the way it looks. You should have clear conceptual knowledge on f dot v concept. You can get many questions on that. Okay. Now you can see it's a parabola. You have two choices. One choice is where the parabola is actually is in this direction, and the second is like this. Okay, now there is a problem in, it's not that straightforward. Now what it tells me is that the power actually becomes fixed after some time. Okay, now let me tell you what is the meaning of this, that the power attains a fixed value over a certain time. Now if you see this question, okay, if you see this question, constant power question, and this is complicated. Okay, just listen to this very carefully. What is the meaning of this graph? This graph is complicated to understand. Understand it properly. What it means is, supposingly I deliver constant power. I deliver you constant power. So I will be forced to use this inverse relationship. But when I apply the constant power concept, I introduce resistive force. Okay, so what happens is that resistive force is now being introduced in a constant power scenario. which means the force on the body and the resistive force, this is the resistive force, kV, right? kV, they become equal at certain point. Initially, it's a constant power scenario. The force is increasing, the force is very high, the velocity is very low, and therefore the resistive force is also very low. Okay, so your power comes out to be equal to the force minus resistive force into velocity. Okay, so initially the force is very high, the resistive force is low, and so you can think in terms of the scenario where at a certain point the force you are applying to the body, okay, and the resistive force, they both become equal to each other. In that scenario, the power being delivered to the body, which you're delivering to the body, so at that stage, the body attains a constant velocity. Okay, it attains a constant velocity. It reaches its highest velocity. A constant power situation with resistive force introduced in it. So this is the expression. And now, as you're progressing, your velocity is increasing, your force is going down, and a certain level, your force goes down so low and your resistive force goes so up that they become equal to each other. And therefore, there is no rate of change of power there, right? Therefore, what you get actually is a flat graph, right? Where the power is no longer increasing with time. There is no rate of change of power, which is the graph of the other parabola, if you notice. Okay, this is the graph I am referring to. Okay, so you can see there is no dp by dt, there is no rate of change of power. The power stagnates at that point of time. Slightly complicated, but I think you should understand it well, because you can expect any question from this. So you should have clarity on the constant power concept and the concept where you have a different scenario where the power is not constant but is a variable, and then how the adjustments happen. So therefore the correct choice is obviously this, but you have to understand each of the scenario. I hope you have read this theory of constant power, what are the graphs, and how do you solve something like this. So in my next video I will come up with some new ideas. I hope you like this from understanding point of view. Okay, I could have solved this in 2 minutes just by writing some equations. I have used the free body diagram. I have compared the situation with a constant power source and with a non-constant power source. So these are two different scenarios. The rate of doing work can be fixed and the rate of doing the work can be variable. You have to approach them in a very separate manner. So I hope this helps you. If you like my channel, subscribe to it and wait for my next video. Thank you very much.